Statisticians are obsessed with being unbiased. This results in some unintuitive formulas, like the formula for the sample variance. The variance is the average squared distance from the mean. So why the heck is there a 1 over n minus 1 instead of just a 1 over n, like a normal average? Why is it not just 1 over n? Let's talk about it. So the variance is the average squared distance from the mean. So here we have two data points. There's a mean, mu, 2.5. Each point has a distance from mu. Each point is 0.5 away from mu. So the squared distance, 0.5 squared, is 0.25. The average of all these squared distances is called the variance. So the variance here is 0.25. But we need to start being a little more precise. You may have heard about the difference between the population variance and the sample variance. But first, we need to start by talking about the population and the sample in general, and also about the population mean and the sample mean. If we have the whole population, statistics is really, really easy. And we don't have much reason to talk about samples. The population is the entire group we want to learn about. There are n, big N, people in the group. We call this the population size. The population mean mu is the average or the mean of the entire population. And the population variance is the average distance in the entire population of each point from the population average, mu. So the population variance, sigma squared, is the average 1 over big N of the sum of all the people in the population's distance from the mean squared. Now, when we introduce samples, things get tricky, so we have to be very careful. One reason they are tricky is because we don't observe the whole population, so obviously we can't calculate the population variance with 100% accuracy at least. And it's also complicated because we usually can't even calculate the population mean, mu. But suppose we magically did know mu. We obviously still can't calculate sigma squared because we don't have the entire population. If we don't observe everybody, we can't calculate the population variance. But we could calculate sigma squared of the sample, where we just take 1 over little n, where little n is the sample size, and we add up all the points minus mu squared. So we did the exact same thing, except we're only doing it for the sample size, n, instead of the population. And this actually isn't a bad idea. It's obviously not always exactly the same as sigma squared, though. But we could call it an estimator of sigma squared, which we often denote with a hat. We could call this sigma hat squared. We just don't see formulas like this because it's unrealistic to know mu if we don't have the entire population. And we don't need an n-1 in this formula. Sigma hat squared is a great estimator of sigma squared. Now let's think about samples, only samples. Suppose we have a sample of little n data points. We call the sample mean x bar, which is just the points added together divided by n. And maybe we could calculate the variance of just the sample. And we could take the average distance, 1 over n, the sum of all n data points in their distance from the sample mean squared. And we're almost to the sample variance. This formula is what we want, except without the n-1. And the question is, why don't we do this? This formula is obviously totally fine if we're just trying to describe the average squared distance of these points from their mean. But let's reintroduce the idea of the population. We want to estimate the population variance, but we can't do it because we don't have all big N samples. We don't have the population. So sigma hat squared was a good estimator, but we don't know mu, so we can't really use it usually. And sigma squared, just the sample, is not that different from that. We just replaced the mu with x bar. Mu and x bar are very similar. But remember that each xi was used to calculate x bar. And that means that the distance xi minus x bar is on average a little smaller than xi minus mu, because x bar is dragged a little bit towards xi because xi was used to compute x bar. So each xi drags x bar a little closer to itself. And now we have enough information where we can clarify a nice thing we would like to be true about estimators that is not true about sigma squared from just the sample. On average, sigma hat squared is equal to sigma squared, the thing we want to estimate. We could write that the expected value of sigma hat squared is equal to sigma squared. And we could prove this algebraically. However, on average, sigma squared, just the sample, is not equal to sigma squared, the thing we want to estimate. And it's because these things are too small, because x bar and mu are not really the same thing. So the expected value of sigma squared just the sample is not sigma squared. And we can try to compensate for the smaller sum here by dividing by a smaller number. So what would happen if instead of using 1 over n, we divide by n minus 1? And miraculously, this works. So if we define s squared, the sample variance, as 1 over n minus 1, the sum of the xi minus x bar squareds, then we can show that the expected value of s squared is sigma squared. So we call s squared an unbiased estimator of sigma squared. And we could prove that s squared is unbiased using a lot of properties of expectation and algebra tricks. But what we're interested in showing is that the expected value of s squared is sigma squared. But if we used 1 over n instead, we would see that it's biased. It's not equal to the thing we want to estimate. There's nothing fundamentally wrong with using sigma squared just the sample with 1 over n. But if we desire to have an unbiased estimator of sigma squared, then we must use the formula for sample variance with n minus 1. And then we can be unbiased. Thanks for watching. Please like and subscribe to learn more statistics.